Right here. Someone has a pointer in the audience?
Hybrid system made of diluted magnetic semiconductors. Probably most of you are not that familiar with magnetic semiconductors, so I will give you a small introduction on this subject and try to motivate people from strongly correlated systems to look at this kind of material. Okay? And then I go on to my results on these hybrid systems. So first, I will give you this small introduction on DMS. Then I will begin to discuss why we want to study these hybrid systems. And we are going to focus on one property of this DMS. This is the Giant Zeeman effect. And then I will give you an example of a hybrid like that, the DMS and a nanomagnet hybrid. And then for my results, I'm going to give you just a few information about vortices and superconductors, information that we will need for the discussion about these hybrids, okay? So, okay, one of the main motivations to study these diluted magnetic semiconductors is spintronics. So while in electronics, we only care about the charge manipulation of the carriers, and we see that in magnetism, we manipulate spin degrees of freedom. In spintronics, we would like to use both spin and charge from the carriers. It means, and sometimes interchange these manipulations. In a way, you can manipulate electrically a magnetic property of a material or vice versa. In an analogy of what we have in optoelectronics, for example. So in spintronics, in semiconductors, we have a lot of issues to study. For example, spin injection in a semiconductor or spin relaxation processes. But there are three important things to look at. For example, new materials that could be used in spintronics and semiconductors, and ways to manipulate spins and produce devices. And this is where the diluted magnetic semiconductors can come and are useful. Okay. So now let's talk a little bit about these systems. In a normal metal, we know that carriers, they play an important role in the exchange interaction between very localized spins to produce magnetism. But in a semiconductor, we don't have, in principle, we don't have free carriers, only if we dope this semiconductor, and we don't have localized spins. So if we want to have a magnetic semiconductor, we must introduce this magnetic moment. For example, doping this semiconductor with manganese. And this has been tried since the 80s or even below. But only in 1997, with a group of Ono from Japan, it was possible to have a ferromagnetic semiconductor made of gallium arsenide doped with manganese. And nowadays we have a whole family of 3,5 semiconductors doped with manganese that are ferromagnetic. So, but when we see the structure of the system, we see that when the manganese is incorporated and substituting gallium in gallium manganese arsenide, it gives not only magnetic moment to the system, but also holes. So it brings not only the spins, but also the carriers. And with only 2 to 8% of manganese in the system is ferromagnetic. I'm going to show you a magnetization curve. So we can imagine that this magnetism is mediated by the carriers, the holes in this case. So this is the magnetization curve as a function of temperature for gallium manganese arsenide. This is an optimal sample. And we see that the Curie temperature is about 175 Kelvin. That's quite high. Of course, it's not room temperature. That's one main issue. And this curve looks very much like a mean field magnetization curve. Very nice one. But this is an optimum sample. Normally, many of these properties are sample dependent in this kind of material. And they have some interesting features, like they are very near a metal insulator transition. The system has a lot of disorder, and disorder plays an important role in this metal insulator transition and actually in the magnetic properties of these materials. So they are quite interesting.
Yeah. Do you know the separation of the moment in vortices?
It's separation.
Separation of the magnetization.
Oh, it's less than, okay, for manganese it's 5 half, but it's a little bit,
Again, 5 half?
no, it's a little bit less, it's less. But it's kind of complicated to calculate this, because when you incorporate this manganese, okay, many of these manganese are not really incorporated, substituting gallium. So they don't contribute to the effective magnetic moment here in this curve, okay?
So they don't create rolls then?
What?
When they are not substitutional, they don't create the rolls, right?
They don't create the roll, so you cannot increase this magnetization. It's a little bit more tricky than what I'm showing here, okay? But it's just a small introduction. So then, but some nice things can be done with these systems. For example, this experimental experiment from Ono's group, where they have dot gate as Claudio was similar to what Claudio was discussing with his 2D electron gas, where they can't control the Fermi level, so the carrier density in this DMS, and we see that you can enhance the magnetism in a system like that, or you can even destroy it by manipulating the electrical properties of the system. And also, it's quite difficult to do that, but it was possible, I think 2 years ago, to apply pressure on a DMS like that, and also manipulate its magnetic properties, okay? So you see that here, if you increase pressure, you see that you have a hysteresis curve, so you have magnetism in a sample that you didn't before, okay? And okay, but how come this magnetism in gallium manganese arsenide, for example? I told you that when the manganese is incorporated, it donates a hole, and these holes, they form an impurity band in the middle of the gap of the semiconductor. And these are the carriers that are mediating the ferromagnetism. They're mediating the interaction between the two spins of manganese. So there is an antiferromagnetic exchange interaction between the carriers and the spins that gives rise to this ferromagnetism. So a good model, at least for gallium manganese arsenide, is just think about an impurity band when you have a hopping term between the impurity sides and the manganese sides, actually, and then the exchange interaction between the holes, the spin of the holes and the spin of this manganese. And someone from heavy fermions background is very familiar to a Hamiltonian like this. And sometimes, depending on the semiconductor, you can even modulate it with a normal Kondo lattice model. So you see that someone from a heavy fermion background can work in this area, kind of easily, okay? So this is just a motivation for. So if you go back actually to the less transparency, where you have this pressure, what we see is that we actually do in a system like that to change the exchange interaction here, and then we enhance magnetism. Okay. But for the hybrid systems, we are not going to need any of these things. Actually, what we need is just a paramagnetic DMS. It means that a paramagnetic DMS has very low manganese concentration. It's from a 3,5 family of semiconductors, or it can be just from a 2,6 family of semiconductors, the old ones from the 80s. They are normally paramagnetic, even when they have the manganese incorporated. So let's look why we want to have this paramagnetic DMS. Because when you have a paramagnetic DMS, even if you apply a small magnetic field, the separation between spin up and spin down states in energy is huge. This can be understood looking at Hamiltonian in a mean field form. Just think that when you apply this field, you polarize the spins, and they act as an effective field for the carriers. But anyway, you have this giant Zeeman splitting, and when the field is slow, this Zeeman splitting is linear with B, so you can think about the ferromagnetic factor of the carriers as being very, very large, huge. So the effective G factor can be 500 for electrons and up to 2,000 for holes. And this is the main feature we want to use when we study hybrids. So why? Because if we think about the Zeeman interaction, and instead of having a constant magnetic field, you have an inhomogeneous magnetic field. This inhomogeneous magnetic field will work as an effective potential that can trap. Imagine that we have a basket like this as a field. It will work like a barrier for one of the spins, and it will work as a well for the other spin. So it can actually trap spin polarized carriers. So now we look at other systems to couple to this DMS in order to generate this magnetic field that has to change in a scale of a few nanometers in order to really trap these spin polarized carriers. Any question about this?
Question. So maybe not about this, the magnetic interaction between the local moments that's mediated by RKKY?
It's not exactly, okay, there is a discussion about that right now, but sort of RKKY. But some people say that is a super exchange interaction. So there is a huge discussion, not a huge discussion, but there is a discussion about it.
Okay, so let me follow up on that by asking, are there any samples that are anti-ferromagnetic? Because RKKY changes sign.
No. Yeah. But the density, the carrier density is low. It's not compared to the metallic sample anyway. Compared to what you normally expect for an RKKY interaction, so it's going to change things. So even if you calculate, but this is a problem because now they are beginning to improve the samples and put more carriers there, and then we don't see this. You could expect the magnetization goes down, but in the beginning, the phase diagram looks much more like this. When you do with manganese more and more, you begin to see a down curve. So it means something like that. But this is an issue, okay?
Can you explain again why you get so high G effective?
I can show you later on if you want to look at some of these calculations, but you can think about a mean field. Just you do a mean field with the magnetic moment, the S, okay, in a paramagnetic state. But you have nothing if there is no field. But if you put a field there, you're going to align, like in a normal paramagnet, you're going to align these magnetic moments. And the field that is these carriers, your field will give rise to this effective effect. I can show you later, but it's not that important for my presentation right now. So,
could be any other magnetic or something very special for manganese. Why manganese?
There could be, but I don't know. People try. Manganese works very well. I don't know. Could be others from the group, but I don't know why. But from now, only have manganese with this distance.
For gallium arsenide, right? If you change the arsenide numbers.
No, but even indium arsenide or indium antimonide, for this group, it's 3,5 semiconductors. Then you have a whole family, but many of these things will not be applied for it.
You have a transition method that works better.
But for 2,6 and 3,5, that's for sure that's manganese. we don't see for the 2.6 and the 3.5. We don't see that many other transition methods working on. Okay. So let's begin with one idea of these hybrids. That you put a small ferromagnetic disk, and it's the magnetization of a disk like that doesn't need to be nano. It's just in order of microns. It's in plane and goes out of plane at the very center of the disk. And in a scale of 10 to 30 nanometers, depending on the material. Okay. So now the field generated by this disk is very homogeneous. So if you put now a magnetic semiconductor on the top of it, you're gonna trap your spin polarized carriers in this small area. Okay. But we could also use a different geometry for the magnet. For example, this rectangular magnet with a magnetization in plane. It goes out of plane in these two regions, the borders. And then if you think about a DMS on the top of it, on the bottom of it, you trap the carriers, but now in only 2 dimensions. So depending on the geometry you have of the magnet, you have a different confining dimension. This is something like a quantum dot, and this is something like a quantum line, but for spin polarized carriers. Okay. So this is the basic idea of using these hybrids. And now, instead of using these magnets, we would like to use a superconductor in a vortex state. Okay, now a superconductor has like 2 important parameters: the penetration depth, that's related to how much the magnetic field can penetrate in a superconductor, and the coherence length is related to the size of the Cooper pair. And depending on the ratio between these 2 parameters, you can have a vortex phase. And if you have a vortex phase, the vortices in a superconductor, they organize themselves in a triangular lattice, where the area of the unit cell of this lattice depends on the inverse of the applied field. So when you change this applied field, you increase this field, you have to populate the system with more vortices, and you have a small lattice parameter, let's say. And there is another important property, that's because each vortex of these carry just half of magnetic quantum flux. So there is just half quantum flux per unit cell in a system like that. And we can imagine that outside the superconductor, these vortices will also generate a very homogeneous magnetic field. And this is the system we're going to study now. We have a DMS quantum well that for us it will be just a 2D electron gas with a very large effective G factor, and on the top of it a superconductor in a vortex state that's generating these very homogeneous magnetic fields that they spread out a little bit outside the superconductor, and then they can trap the spin polarized carrier. Just a comment about this 2D electron gas. If we compare it with the 2D electron gas that Claudio was talking about before, in this case, imagine you put a perpendicular magnetic field in this 2D electron gas with this effective G factor. Now I have a different situation where the distance between the Landau levels in energy is very small compared to the Zeman splitting. So the Zeman splitting is really large, and the Landau level separation is very small. Just to give you the idea of what it means to have a very large effective G factor. So, okay. So this is a system, and what's the advantage of using this system? Because it's also generating this non-homogeneous magnetic field. Is the fact you can manipulate vortices in a superconductor in a way you could not do with your magnets. So when you apply a current in a superconductor, you move these vortices, and there is a huge field of physics on manipulating vortices in a superconductor. So now we're going to look at 2 different limits One is that when you have a very low applied field, we have very few of these vortices nucleated in the superconductor. So the carriers in the DMS, they feel the field of just one isolated vortex. And then we're going to look at the bound states here. And then there is another limit that's quite interesting, that when you really have a triangular lattice of vortices, the 2D electron gas will feel this effective periodic potential. And we're going to look at, you're going to see that we can look at transfer property signatures of this lattice in the DMS.
So if you look at the concept in the other spin polarization, don't you generate an artificial lattice? Can you look at this as a way to generate?
Yeah, it's going to be like that. We're going to look at something like Hofstadter butterfly thing. We are generating an artificial lattice in the DMS.
Do you think that the vortices are going to be more trapped in this case than just a normal superconductor?
I don't think so. Because of the manganese?
Yeah, because now maybe you have more of a trapping potential, like a stronger trapping potential, because you have this other material.
Maybe, yeah. Maybe depending, yeah. Maybe it's we have to actually have to calculate how for example, the manganese here can change but I think the scale is different because these vortices are kind of big compared to, for example, the size of the impurity. So in each of these regions, you have a large number of magnetic impurities. So this was the question. So now, let's look first at the isolated case. So here, you see this magnetic field spreading out outside the superconductor. And this is more or less how it looks like. So here you have the Z component. I'm not spending so much time in this slide, okay? So we have the Z component of the magnetic field and the radial component of the magnetic field as a function of some parameters like the ratio between this, the coherence length and the penetration length, and also as a function of the distance between, the DMS and the superconductor. So that's radially symmetric. And we can look at the Hamiltonian of this system, and here we have this effective potential, and we see that the field really looks like a basket. So we're going to trap one of the spins, and we'll work as a barrier for the other. And in this case, the vector potential doesn't play an important role because the wave functions die much early, in space before this term would be important. So this is not important. We calculate with this, but doesn't matter. It's more or less the same. The energy spectrum is more or less the same. And here we see that we really have bound states in a system like that, and as a function of many different parameters, like that ratio I was talking before. These are the three lowest states. And as a function of the distance between the DMS and the superconductor, and also as a function of the product of the effective mass times the zero magnetic factor. But if you have a heavy particle there, then you of course you trap it more easily.
Energetic, you can drop that off, but since it's a pi flux, right? It's a half flux, right? Doesn't it change the boundary condition when you solve the problem?
No, because the problem is that the wave function actually penetrates inside the flux. So, because the Zeman interaction is so strong, what happens is it dies, it goes to zero before having this problem. Can you understand?
But in the other direction, the angular direction,
yeah.
You have to take anti-periodic boundary conditions for the wave function as it goes around because of the flux.
No, it's not. This is what is not really necessary because we have this flux, but the wave function, it goes to zero inside the region that we still have effective, strong effective potential. So really the flux, this part of the Hamiltonian doesn't really matter that much.
But isn't there a Nerva-Home effect?
There is not, because it only if the G factor is smaller than 2. Okay, but in this case, this effective G factor it's smaller than 2 point something. Okay, but there is a transition. If you have a G factor of 500, the Zeman term plays a much more important role and kills the other. But only in the isolated case. You're going to see that when you look at the lattice, this is different. Then you have to take care of these things. Okay. But you know, I lost some nights because of this in the beginning of the project. I'm very sure about this. So, and then you can look at the localized states, and we see that the contribution for spin up and spin down is very different. So we have a strongly spin polarized state. I forgot to mention, but it's not 100% polarized because we have the radial component of the magnetic field that will make spin up and spin down. So that Hamiltonian that I was showing before is actually, you have to solve it, you have actually a system of two equations that are coupled, and you have to solve them for spin up and spin down, okay? So, you know, okay, good. We can have spin polarized carries back there. So the basic idea now is to try to manipulate these things by, for example, applying a current, and then because there exists a lattice force, it will move the vortex perpendicular to the current and perpendicular to the field. And you can lithograph the superconductor in a way that the vortices, they tend to nucleate where you have a thin layer of superconductor. So you could build a device like this. And now we are trying to study a system like that, where you have the same lithography, but there is a hole here with two vortices. They try to be far apart because they repulse each other. And then when you apply a current, you make they not collapse, but you know they proceed. And then you can calculate the magnetic field in each of these configurations. Now in a collaboration with Peter's group in Belgium, they know very well how to calculate all these fields. And now we are looking at the wave functions in this situation, and to see when we have a superposition, we don't know if the electron now is in one or the other vortex. Okay, so this is the idea. The continuation of the project is to try to now begin to manipulate these states. Now, this is for the single vortex. Now we're going to talk more about this lattice problem, and then you know. You are right, Claudia, now we begin to think about all these effects. So now, if you keep increasing the magnetic field, we really have a vortex lattice, and this is just, I'm plotting here just the modulation of this field. So it's the field minus B0, only the modulation of the field. And we see that for low fields, the modulation is quite high, so we have a kind of deep periodic potential. We keep increasing this field, and you change the distance between these potentials, but and now we have a potential that's not deep at all. Okay. So if you want to look at what's happening at the DMS, we can look at. Okay. Can you hear me now? Tem que ligar? Oba, tem que ligar? Não. Vou tirar o caixão. Okay. So now, if you look at the DMS, okay, we have two important limits that we were discussing a few minutes ago. So for very low magnetic fields, where you have the isolated vortex, the energy spectrum is the one that I was showing before. But then imagine that we have very, very large fields, a limit of high fields. It's a 2D electron gas plus a perpendicular magnetic field, so we have Landau levels. Just be careful that, I was talking before that these Landau levels are a little bit different because now, first we have the Zeman splitting that was produced by B0, and then the Landau level. So these levels are also spin polarized, okay? But in the intermediate case, we have a funny thing because this field, it's working as an effective periodic potential, an artificial potential, let's say. So let's try to look at this problem and look at the Hamiltonian. So now the Hamiltonian, this is the Hamiltonian, and now be careful because we have to take care of this term. If you can write down this, the magnetic field in two parts, the constant part, that's actually B0, the applied field, plus just the modulation, that was the one I was showing the last picture, and then we can write the vector potential associated to each of these contributions. And this one is the one that's not important because it's periodic as well. But then this term will play a very important role because it's linear with x. So in a lattice, this will be like really, really important, and it will give rise to a phase in the wave function. So if we try to construct a solution in a normal way, where you have like the translation operators, you're going to see that your Hamiltonian will not commute with the translation operators. And more than this, your wave functions will pick up a phase that will depend on the flux that's enclosed by the unit cell, okay, or artificial unit cell. Okay, so for those who knows more or less what we're talking about, we have three ingredients here. We have a 2D electron dance, a perpendicular field, and an artificial periodic potential. And as a consequence, you have this phase that depends on the flux enclosed by the unit cell. So this is what is known by the Hofstadter butterfly problem. I will going to talk about this in a few minutes. But in this specific case, it's more than this, because we have a triangular lattice, so it will be a Hofstadter butterfly in a triangular lattice. But more than this, we never go away of the ratio between flux, the ratio of 1/2 of flux per unit cell, because this is a property of superconductors. Doesn't matter if I keep increasing my field or I decrease my applied field, I end up always having 1/2 of flux per unit cell. This is very strange, okay, for this effective potential. So it's like looking a Hofstadter butterfly problem in a triangular lattice when you sit down in one of these lines and you see what's going on. But then we can change, the deepness of the potential. You can go from a weak perturbation of these Landau levels to the other limit, but always sitting here. Okay? But
so the additional flux if you have more magnetic field.
What?
If you apply a bigger magnetic field.
Doesn't matter, because what happens in your system is that you nucleate more vortices. You change the lattice constant, but you keep the same ratio between flux and lattice, flux per lattice. This is a property of a superconductor. For each vortex, you have 1/2 of quantum magnetic flux. You see? Until inside the vortex phase. If you go over here, of course, this is different. Okay? So now, let's talk a little bit about this Hofstadter butterfly for people who doesn't know this very technical term. So imagine, now let's go back to Claudius' first class. He was talking about quantum Hall effect, the integral quantum Hall effect, and so he calculated the energy for each Landau level. He talked a little bit about the wave functions. Here I'm using the Landau gauge, so it's a little bit different. But all these things were discussed. So the ratio between flux and quantum flux being P over Q was discussed, and so on. So now imagine you include the periodic potential in your system, okay? And in a similar way, let's forget now all the other levels, let's keep the n equals 0 level, okay? If we do that, and we try to calculate, do a perturbation theory on this periodic potential, imagine it's just a perturbation. What we see, I'm not going into details here, but we're going to see that this perturbation will not be diagonal in different ky vectors, and you end up having, to solve this problem, having a Hamiltonian matrix that's periodic in P. So it's going to, instead of him having just one line, you're going to really have like a matrix to solve this problem, and you end up obtaining that this periodic modulation that was introduced, it splits each Landau level in terms of P subbands, which now are key-fold degenerate. So you lift the degeneracy of the Landau level and breaking it in many subbands, which now have only are key-fold degenerate. This is the normal Hofstadter butterfly. Okay, and when you do that, you have, and this depends on the number. Let me go back. So as P and Q are exactly the ratio between the flux and the quantum flux, it depends on the flux you have in your system. So depending on the flux you have in your system, you can have, instead of your Landau level, you can have many mini bands. So here, for example, is 1/3 of flux per this ratio is 1/3, and you see that you have 3 subbands. So there are ways to split this many subbands. So this is why it's named Hofstadter butterfly, because if you plot this nice plot, you see a structure that looks more like a butterfly. And also, we could do this calculation in a completely different way and begin with a tight binding Hamiltonian and put a very small applied field. And you also split your tight binding band in subbands that will depend on the inverse of that ratio. And so you're going to have an equivalent or complementary butterfly. So you can go from the limit of high fields and you construct your structure, you can go from the limits of very low fields, but you have this periodic potential, okay? And you can also see signatures. I'm not into details of this, but you can have signatures of this butterfly that looking at magnetotransport measurements, because the quantum Hall effect, the interior quantum Hall effect, in this system is very unusual because each of these gaps between mini bands has a Hall conductance associated to them that's different than 1. Can be 2, 3, 4, minus 1. So the jumps in the Hall conductivity will be very, very strange. And this is a result for von Klintzing's group from 2004, where they can see in this problem of the Hofstadter butterfly signatures of these mini bands. So in our problem, we have not exactly this situation, because when you change the applied field, we always have the same ratio of flux per quantum flux because of the property of the superconductor. But anyway, we can use all this information to construct a solution. So what we do is we use the magnetic translator operators, they are modified translator operators, and they only commute when there is an integer product of the quantum flux per unit cell. So in our case, we doubled our unit cell in order to solve this problem. And we want wave functions that are both eigenstates of the Hamiltonian and this translator operator, magnetic translator operators. And we construct our basis, a wave function using a basis constructed from the Landau levels. So now we have something different from the case I was talking before about the Hofstadter butterfly, that normally you only use one of the Landau levels and you do a perturbation theory. Here we don't do that. We use as many as possible Landau levels in order to produce our results. Okay, so we have this effective potential, and we mix all kind of states to construct this basis, and we go up to 100 of these levels. Oh, this is and then you can integrate the R part of this thing, and you end up with a matrix. We have to diagonalize a matrix that will give you this D, K-dependent D. Okay. So then we get this energy spectrum for the limit from the limit of very low fields to the limit of very high fields, using this approach of mixing all these Landau states. Okay. So here, for example, is a limit more or less a tight binding limit. Okay. We have, if you remember, the three lowest levels looks very much like them. Here, these numbers are the associated quantum conductance, Hall conductance, that I'll discuss a little bit later. So here you see that you have this the gaps, large gaps, and in this part here, what you see that you split this tight binding band in two. This is a signature of this Hofstadter butterfly, because when that ratio is 1/2 in the tight binding limit, what we know is that your tight binding band is split in two. If it was like a square potential, we could not see this signature, but as it's a triangular lattice, we know that there is an opening of the band, and we can see that. It's very clear. And even the Hall conductance associated to this splitting is the same that we find in literature. And here we see these two bands, they really look like tight binding bands. And then if you keep increasing this magnetic field, you see the variation in field is here. You see that we begin to mix all these bands, and you begin to recover a structure that looks like the Landau level bands. And here in this situation, you already recover the normal quantum Hall effect. So if you say 1, 2, 3, 4, 5, 6, 7, these are the Hall conductance. We see that they can be very strange. Okay. So, and this only happens because, again, in this ratio of quantum flux per unit cell, in the limit of including the periodic potential as a perturbation, in this specific situation, we don't have the opening of more bands. But if you had a different, instead of having a triangular lattice, we could have, for example, a square lattice. We were going to see more structures here, breaking up each of these Landau levels. Okay.
Is it possible to construct a square lattice if you bend the superconductor so as to trap the vortices? Is it possible?
It's possible, yeah. Then it's a little bit, yeah, it's possible. But then when you keep increasing the field, sometimes you modify this lattice, and it's not more square, but has a vortex in the middle. But you can do that. It has been done. And you can even change instead of having a vortex of half a flux, you can have more, because then you nucleate. When you pattern this superconductor, you nucleate two vortices in one.
I thought you said in the previous slide that if you have a flux which is P by Q, then you split it into P subbands which are Q4 in degenerate. But here you have half a flux quantum, so I would expect it to be two subbands which are each non-degenerate. But you seem to split it into
Sure.
No. So Q, sorry, I said it the wrong way. So P by Q is then...
Oh, but there are two limits. Here, okay. Remember that I told you that you have the complementary butterfly? Because that first calculation is an easy way to see that you have this butterfly, but I was going from the limit of Landau levels, high fields, and a perturbative potential. In this situation, I have the opposite. I have a tight binding band with a perturbative magnetic field. So then it's the other way around, okay? So it's a little bit tricky. It's not that complicated, but you know, if I was going to explain using the tight binding model, it was going to be very complicated. That transparency there. So okay, so here we can calculate. So we can calculate the energy spectrum, but also we can calculate the quantum Hall effect. That I will not enter in these details on the calculation, but it has to be with the topology of the Brillouin zone and how these wave functions they will have some, in some points the phase of the wave function will be not well defined. So then you can find winding numbers of this phase. I can show someone that's interested, but in principle I'm not discussing this here. But what we can do is we can calculate the Hall conductance of this whole phase diagram from low fields to high fields and vary actually the density of carriers. And these are the colors are the gaps, okay? And these white regions are the bands. Sometimes the bands, they touch each other, okay? So this is why you have this sense here. In this area, of course, we cannot define anything. But anytime you have separated bands, you can calculate the Hall conductance of each of these gaps in this whole region. And from that, you can construct, for example, any Hall conductivity as a function of field or density you want. And in this particular case, we walk around this line, and then we can construct this type of jump. So we have a jump of 3, then 1 more, and then goes back to 3. And all these numbers, they came from the calculation of the quantum Hall conductivity, okay? So I'm going to finish my talk now saying, okay, so what we got? We got that the Zeman induced, the Zeman effect is able to localize spin-polarized carriers in a DMS, and using a superconductor, it's possible to manipulate these states by, for example, vortex dynamics. Also, an important feature of the system is that in the lattice case, because of the property of the superconductor, we induce a Hofstadter butterfly energy spectrum in the DMS, but with a very interesting property that we always see in this 1/2 ratio. That normal thing is, in a normal Hofstadter butterfly case, when you change the magnetic field, you always change the flux per unit cell because it depends on the magnetic field. But in this case, it's a very strange situation where you don't change. Now, some other basic problems could be studied in a system like that. Okay, this is one example of source of non-homogeneous magnetic field, but there are many other possibilities of generating a non-homogeneous magnetic field in a very small scale. So you could, in principle, you can construct other devices that could do other things if they produce a very homogeneous magnetic field. So that's all. Yeah.
10 minutes ahead of schedule, so question.
Do you have to worry about spin recoupling in this system?
Yeah, good question. You have. This was made with using a simple parabolic band, okay? But you can do. Remember when I was talking about the DMS with the nanomagnets. In that situation, we use a Luttinger Hamiltonian, considering all the bands of the band structure of the semiconductor. There are some work on the whole Southern butterfly using this band. So we could do that here.
But
of course, these jumps could change a little bit, but the main physics of the system is more or less the same. You see.
But all what you showed was without including this spin orbit coupling.
The results, yeah, we have, remember the first transparency when I was showing this nanomagnets, we have results for that. I was not showing here each details. That we use this, the spin orbit coupling. But here is for a parabolic band. But of course, you can write the same program using more bands.
So have people observed some of this experimentally?
Not yet. No, it's. I think for the second part it's more difficult because then you really need a nice 2D electron gas made of DMS. You can produce 2D electron gases in a DMS. You cannot actually see quantum Hall effect and everything. But this is one thing. The other thing is to couple this with the superconductor. But for the other limit of manipulating these vortices, I think it's more easy to do. And there is a group in Argonne trying to grow the superconductor on the top of the DMS and make all these contacts. But the problem of contacts is complicated.
More questions? No, let's take this clear game. Just a reminder, since we started half an hour later, so we're meeting here again at 3:30. There are 2 more speakers this afternoon, Piers and, forgot the last one, sorry. And then a discussion at the end.